Hi everyone! Today let's talk about section 14.4, Green's theorem. So first let's talk about divergence and curl in two dimensionals. Suppose a vector field represents the fluid's flow. We might want to analyze how fast the field is moving in various ways at the points in its domain. For example, we might want to measure how fast the field is flowing out away from a point. Or maybe we want to measure how fast the field is rotating around a point. So these measurements involve taking two different types of vector field derivatives called divergence and curl. Okay, so 2D divergence. Given a vector field f of xy, let's say the coordinate function are f and g, right? And then the two-dimensional divergence equals fx plus gy. So partial f partial x plus partial g partial y. The geometric interpretation, okay, so we have a point here. We want to measure the net rate at which the field is flowing away from the point. Okay, so we want to measure how much vector field is flowing away from the points. Okay, so if the divergence is positive, then we have a net outward flow. If the divergence is negative, then we have the net inward flow. So flowing in. So far, so good, everybody? Okay. Intuitive way to think about it. So imagine drawing a very small loop around the point. So here we have a point. If we draw a small loop around it, if there is more fluid flowing out through the loop than the fluid flowing in, okay, then it means the divergence is greater than 0. Okay, so if it's more fluid flowing out, then we would say this point is a source because there is a net outward flow from the point. If instead the divergence is negative, then we would say the point is a sink because the fluid flows inward, so it's a sink. Can you imagine it's like water and then flowing out from a point and flowing in? Okay, so if the divergence is 0 at all points of a region R, then the vector field is called source free on R. Okay, so source free means divergence of f is 0 at all points. Okay. All right. So this is divergence. So we measure how much fluid is flowing out. Okay. How about 2D curl? So for vector field f equals f and g, the 2D curl is gx minus fy, so partial g partial x minus partial f partial y. The geometric interpretation, so it measures how the net rate at which the field rotates at the points. So we want to measure how much vector field is rotates at the points. So far so good. If the curl is positive, then we have the counterclockwise rotation. If the curl is negative, then we have the net clockwise rotation. So intuitive way to think about it. Imagine placing a very small paddle wheel at the point xy in the fluid field. If the fluid field makes the paddle wheels rotate in the counterclockwise direction, okay, then we have the curl is positive. Have you ever played a spinning top? Yeah, so it's spinning, or it can also spin in the other direction. Okay, so if the curl is positive, then it spins in the counterclockwise direction. If the curl is negative, then it spins in the clockwise direction. Okay, if the curl is 0 at all points on the region, then we say the vector field is irrotational. Okay, so it's not rotating at any point. So irrotational. So far, so good, everybody. So if divergence 0, we call source-free field. If the curl is 0, we call it a rotational field. Okay? Alright, let's look at some example. So consider the vector field f of xy whose plot is shown below. In the windows x, so x is between -2 and 2, and y is from -2 and 2. So you can imagine this is x, this is x, this is y, this is -2, this is 2, this is -2, this is 2. Okay, this is a 0. Using the picture, estimate if the curl f and divergence f is positive, negative, or 0 at each of the points. So let's see. At 0, 0. At this point, okay, what is divergence? We measure whether it's going out. Okay, so going out. Well, do you see the arrows? Are they pointing out? Yes. We do have an outward flow, so here divergence of f is positive, right? Do you see it rotate? No, it's flowing out, but it's not rotating. So we can see the curl is 0. So far, so good? Alright, let's look at the next point. At the point 1, 0. Where's 1, 0? Oh, here. Okay, what can you see? Well, do you see this arrow going in, but this arrow going out? So we have some arrow going in and we have some arrows going out. Actually, in this case, I would guess the divergence is 0 because we have 2 arrows going in and 2 arrows going out. So the divergence is 0. So far, so good? Okay. And how about the curl? Well, you can see it's not rotating, so I would say the curl is also 0. How about at the point 1, 1? Well, 1, 1 is right here. Can you see the arrows going in? So because we have an inward flow, the divergence will be negative, inward flow. And is it rotating? No. So the curl will be 0 as well. Okay, and it turns out f, this is the vector field formula for f. So verify part A using the formula. Okay, now let's see. This is fg, right? What is divergence? fx plus gy. Right? fx derivative of sine is cosine pi x chain rule, so times pi, right? And then plus derivative of sine is cosine pi y chain rule, derivative of pi y is pi. Okay? And how about the curl? The curl f. Okay, so that is gx minus fy. Okay, so gx, is a function of y, so gx is 0. Fy, f is a function of x. Fy is also 0. Oh, the curl is 0 everywhere. So you can see, because it's 0 everywhere, we know f is irrotational. So far, so good? Okay, now let's see at 0, 0. The divergence cosine 0 is 1, right? So we get pi plus pi, which is 2 pi. See, it's positive, so it matched with our guess. And at 1, 0, what's the divergence? Well, cosine pi is minus 1, cosine 0 is 1. Oh, you see, they cancel out. We actually get 0. And at the point 1, 1, cosine pi is negative 1, cosine pi is negative 1. So we indeed get a negative divergence. It matched with our guess. So far, so good, everybody. Do you have the same answer? Okay, so I also hope that when we go over these examples, you can try it first. Yes, so feel free to pause the video and try it first. So compute the divergence and curl of the following fields. All right, now let's see. Okay, let's look at the first one. What's this? So this is F. This is G, right? What's divergence? Divergence is fx plus gy. Fx, or x minus y derivative with respect to x is 1. X with to the derivative of x with respect to y is 0. So that's 1. Okay, is it going in and going out? Going out. Yeah, it looks like it's going out. Okay, and how about the curl? Well, you see, I think it's spinning, it's rotating counterclockwise. I would say this is positive from the picture. Now let's see, gx minus fy, sorry, fy. Gx is 1, fy is minus 1. Oh, you see, it's 2, so it's rotating counterclockwise. So far, so good. Do you have the same answer? Alright, let's continue. Okay, and you can see they are constant numbers, so which means at any given point, the divergence and the curl are going to be the same. So divergence is 1, curl is 2. Okay, continue. So this is f, g. Divergence of g is then fx plus gy. Fx is 2x, gy is 2. Okay, and the curl. Okay. This is g, not f. Okay, gx minus fy. Gx 0, fy 0. Oh, this is 0. So it's not rotating, so it's irrotational. Okay, so the field is G is irrotational. Okay, however, the divergence depends on the x coordinates. So far, so good, everybody? Okay, so let's continue. Alright, so we have discussed the following 3 types of integrals. So I'm gonna make a summary of you. We have the line integrals, okay? So here we have the work or circulation integrals. Okay, so we have the vector field, we dot product with the unit tangent vector with respect to the length parameter. Or we usually use this formula, okay? F that's the derivative of the displacement. So this gives us the work or circulation integrals. If F is a force, then we have work done, and if F is a fluid flow, then we have circulation. So far, so good, everybody. And we also talk about the flux integrals. Oh, what's the circulation integrals? So we have a path, right? We want to measure the components of F in the direction of the path C. Okay, where the flux, we want to measure if the orientation of C is this way, we want to measure how much the vector field is going across it from the left to the right, okay, of the vector field. So how we calculate, we use f dot n. N is the normal vector. This is t equals k. Okay, but usually how we calculate, we use this formula to calculate. F dy minus g dx. Okay. And we also talk about the double integral. Well, we have a region on the xy plane. So this is R, and then we want to measure what is the volume under the surface F on top of this region R. Okay. So the next theorem that we will study is about a deep relationship between this type of integrals. So first, let's look at the 2D curl and the work or flow. Okay, so what is the relationship between the 2D curl and the work or circulation? So for a vector field F, we define the curl be gx minus fy. If we think of F as representing the velocity field of a fluid in the xy plane, and then the curl measure how fast the fluids rotate in at the points in counterclockwise direction. So here we have the points, okay, counterclockwise. This is the direction. Imagine C is a small closed loop center at the point xy. Then, well, when you measure it, well, do you see this rotation? It's like you want to measure like how much vector field are going along C. Okay, so curl equals, this is a circulation line integral over the small area change of A, right? Okay, so this is how we measure like how fast the fluids rotate at that point. Okay, we imagine the circulation along the path C, okay, over this area. So if C is very small loop enclosing a very small area change of A, then this work or circulation is approximately equal to curl times change of A. Okay, so look at the following example. Let fxy be a field with curl equals 1 minus x squared minus y squared. Estimate the counterclockwise circulation of F along a circle with radius 1/10, centered at each of the following points. Okay, so first, at the point 1, 1, what's the curl at the point 1, 1? Well, x is 1, y is 1, so our answer is minus 1. Then we know our circulation is approximated by the curl at that point times the area of that little pieces. Okay, so the circulation is minus 1 near the point 1, 1 at the point 1, 1. And what is that area? Well, that is a circle with radius 1/10. Okay, so circle pi r squared, but r is 1/10 squared. So our answer is minus pi over 100. So this is the circulation, counterclockwise circulation near that point. So far, so good. Okay, how about at the point 0, 0? Well, at the point 0, 0, the curl at that point equals 1 minus 0 minus 0. So that equals 1. Then what is circulation? Circulation is approximated by the curl at that point times, where do I make? Okay, this small area. Alright, so the curl is 1 at that point. And our small area, this is a circle with radius 1/10, so it's pi r squared. We get pi over 100. So that's the circulation. Okay. So far, so good, everybody? Yes. So this introduces our theorem. Yes. Okay. So those are just estimates. we can do much better with the same given information. Here we have the Green's theorem, circulation form. So actually, Green's theorem, we have two forms, circulation form and the flux form. Circulation, we kind of relate the curve, because think about it, a curve. Well, we're talking about the how much vector field are flowing in the direction of C. This is circulation, and then here is like we're measuring the field rotating counterclockwise, right? So that's curve. So circulation form involve circulation and curl. Okay. So it's about circulation and curl. Okay, and we have flux form, so we'll talk about later. So flux form. Okay, so this is the point. Well, what's divergence? Well, divergence measure like how much vector field flowing out of the point. Well, then this is the curve C flowing out. You see from left to right. This is exactly flux, right? So it kind of relates flux and the divergence of F together. So Green's theorem, we have two forms: circulation form, which relates circulation and curl, and we have flux form, which relate flux and divergence. So once you draw the picture, then you can tell. Okay. So we have some assumption. So given that C is a simple, closed, smooth curve in the xy plane, oriented counterclockwise. R is a connected and simply connected region in the xy plane that is enclosed by the curve C. F is a vector field. The coordinate functions are f and g. So both f and g have continuous first partial derivatives in R, in the region R. So this is the picture. So circulation measures how much vector fields are going in the direction of C. So going along C. Okay? And the curl is we want to measure like counterclockwise. Okay, so the Green's theorem in two-dimensional give us the following facts. The circulation along the paths, the simple closed curve C equals, so all of these are the line integral. Okay, the circulation formula. Okay, so the Green's theorem tells us that this guy equals to the double integral of the curl over the region R. And how do we get that? Well, it is from this guy, right? So here. So because the circulation on C is approximately by the sum of those curl of F times change of A. Well, this sum is actually the double integral. And then we have curl of F, and then this is the area differential. So far, so good, everybody? Okay. And what's curl? Curl is gx minus fy, partial g, partial x, minus partial f, partial y. Well, so the Green's theorem actually kind of related one-dimensional line integral and a two-dimensional double integral. Isn't it amazing? So roughly speaking, the Green's theorem says that the following two quantities are the same. First, the net circulation of the fields along the curve C, which is the outer boundary of the region R. Okay, next, the net rotation of the field F over the interior region that is bounded by the curve C. So these two quantities are the same. Okay, So note that Green's theorem established the test for conserved vector fields. Okay, that we discussed earlier. So if curl, okay, remember for conserved vector fields, we require Fy equals Gx. If that is happening, then the curl Gx minus Fy will be 0. Okay, and because now the curl is 0, so that's why for any loop, oh, you see this symbol? If we have a circle there, means it is a loop. It is a closed loop. Okay, so f dot r, if f is conservative vector field, then the curl is gonna be 0. So that's why we get the circulation of a closed loop, okay, is 0. Okay, so far so good, everybody. All right. Yes, and we also have a theorem that if the circulation is 0 for all simple closed curve, then F must be a conserved vector field. Okay. Next. So hence we have F is conservative, then the curl of F is 0. Okay. However, the converse statement is not true in general. So so to be conservative, we have two conditions. Okay. So if and only if so two conditions. Okay, so test for conservative. So first condition, Fy equals Gx, remember? And second conditions, the region R is connected and simply connected. This is a test for conservative vector fields. Okay. That's why the curl is 0. Okay, if the curl is 0, if only have one condition, but the second condition is not satisfied, the vector field might not be conservative. And we talk about example in our last class. Okay, so the converse statement is only true when F is restricted on a connected and simply connected region. Okay, so we call that irrotational vector fields are vector fields with 0 curl. Okay, so conservative vector fields is a subset of the irrotational vector fields. So if we want to draw like a subset relation, then we have the bigger set is the irrotational vector field. Okay, then the conservative vector field is a subset of it. Okay, so our last example in session 14.3, we have shown it is a rotational. The curl is 0, so it is an irrotational vector field, but it is not a conservative vector field. Do you remember that example? So let me copy down here. Okay, so that one that vector field was minus y over x squared plus y squared, and we have x over x squared plus y squared. Okay, so this guy is irrotational, but it is not a conservative. So far so good, everybody. Okay, let's continue. Let's do some example. Okay, so let F be a vector field in the xy plane. Suppose for all xy points in the xy plane, the components of the field satisfy the condition gx minus fy equals 1 minus x squared minus y squared. Is it possible that the field F is conservative? Explain why or why not. Wow, the curl. That's the curl, right? So A, the curl of F is gx minus fy. It equals 1 minus x squared minus y squared. So this is not 0, then of course it's not a conservative vector field. Okay, so F is not conservative. Okay, because if it is conservative, then the curl must be 0. So remember, if F is conservative, that implies the curl of F is 0. The contrapositive of this statement is also true. What is contrapositive statement? It means if the curl is not 0, that implies F is not conservative. However, the converse statement is not true, okay? Because last time we found an example that a vector field, the curl is 0, but it is not conservative, okay? Part B. Let C be the unit circle, oriented counterclockwise. Find the integral. Oh, okay. So that's the circulation, right? So C is the unit circle, oriented counterclockwise. We have the parameterization for it. Do you still remember? That is cosine t, sine t, right? And t is from 0 to 2 pi. Yeah, we have this circle. Like we have done so many examples about this circle. Okay. Now what happened? So we know here the circulation is actually equals the double integral on this circle of our curl. Our curl is 1 minus x squared minus y squared dA. So far so good. So actually in this problem, our vector field F is not given, so we cannot use our regular way to compute the line integral. Okay, so we gotta use the Green's theorem. So we can say by Green's theorem, the circulation equals the double integral of the curl. Okay, now what is the region R? Well, this is the region R, right? And it's better to use polar coordinates because we're working with a circle. So polar coordinate, well, you know, x squared and plus y squared, that is r squared. And polar coordinate, we have r d theta. Our theta is from 0 to 2 pi. Our r, because it's a unit circle, r is from 0 to 1. Well, we can distribute, right? Yeah, we don't need U substitution, even though U substitution work here, but we don't need it because we just multiply out and then we can just use power rule to compute. So this is r minus r cubed dr d theta. Integral of r is r squared over 2. Integral of r cubed is r to the 4 over 4. We evaluate from 0 to 1 and then d theta. Okay, so we plug in 1, we get 1/2. Minus, we plug in 1, we get 1/4. When we plug in 0, they're all 0. So 1/2 minus 1/4 is actually 1/4, right? Integral of a constant with respect to theta is just theta. Evaluate from 0 to 2 pi, so we plug in 2 pi, minus we plug in 0. Oh, what is our final answer? Our final answer is pi over 2. So far, so good. You can see this is not conservative because the line integral of a closed loop is not 0. We can also see from here. So far, so good, everybody. Alright, so let's continue to do more examples in video part B. See you soon. Bye.